vector models and dynamic fault trees using biographical reactive systems by P. Govind Raj and Subrat Kar. So, if you please.
Hope I was audible before. So this is a joint work. I mean, this is a PhD work with Professor Subrat Kar. He's my supervisor, and this work is at the Indian Institute of Technology, Delhi. And what we are interested in is formal modeling for cognitive buildings. And what I'm going to present here is basically an extension of the work that I presented in the previous version of the Formal Methods Conference. So what I plan to do here is basically to give a high level introduction into the entire research and how we are placing the research. And the details are more into why we are doing this, and the paper has more details into how we are doing it. Okay. So, but I'll be happy to discuss the implementation aspects of it if anybody is interested. So we'll go with what the motivations are and what the backgrounds are. I'll give a brief of what Actors at BIM is all about. And I'll talk about specific extensions to the formal model that has been proposed in this part of the work, and then I'll conclude. So basically, a cognitive building is a paradigm shift from the static view of a building. Generally, as it's always considered as a container of human activities. But cognitive buildings are basically cyber-physical systems which are embedded with sensors, actuators, and computing elements. And it works by sensing, controlling, and actuating the built environment itself, right? So this could be smart offices or smart buildings, or a conference room which could change its shape with respect to the kind of exhibition that it hosts, for example, using sensors, actuators, and things like that. And what we want to do is we want to formally model such a built environment. The basic motivation for doing this is that there is a requirement for formal modeling and studying such aspects. And there has been prior attempt to do this, there has not been a cohesive model which captures the various facets of cognitive building in unison using the same meta modeling framework. And that is what we are trying to do. And what we're trying to do here specifically is to have a tower of informatic models. And each of these models is a formalism which caters to a very specific aspect to model the building. And these models are related to each other in a very formal sense, using the notion of category theory. And a tool, along with a programming language, which can be used to apply this modeling in real life scenarios. So I would like to start with what bigraphs are. If you look at bigraphs from a mathematical perspective, the first definition that you will get is a bipartite graph. But we are not talking about a bipartite graph here. What we are talking about is bigraphs in this sense, wherein the top, this is a bigraph. And why it's called bigraph is because it has got two components. One is a forest, which is basically a group of trees, and other is a hypergraph. Now, this forest models the notion of containment. So, for example, a building has a room has a computer, and things like that, right? And this hypergraph models connection. Okay, so this computer can be connected to that computer, which may be in some other room. So it models two distinct notions in a single structure, so as to say. Now, so this is an example of a built environment. So here we see that there is a building called B, within which we have 2 rooms. Within each room, within this room, we have got an agent called A, which is connected to a computer called C. There is another room here. Again, we have an agent here, and we have a computer here. And both of these computers are connected through a network R. And there is some room somewhere else, which is not a part of this particular building, but all these agents are communicating with each other, right? So this gives you a structure or the space, as you would like to call it. Basically, you're modeling the static aspects of the cognitive environment. Now, where does the dynamic part comes in? The dynamic part comes through what is called as reaction rules. And these are rules as to how this graph can be transformed, right? So you can give specific rules, like, for example, an agent can enter a room, okay? So the agent was outside the room, the agent can enter this room. And this, when applied to a modeling environment like that one, so this graph here transforms into something like this. Okay? So here, this is the before and this is the after. So when you're modeling this, what you're trying to do is that you're giving a static representation of the concept that you're modeling, and you're providing reaction rules as to how the system evolves, right? The other thing that you can do is basically compose things. So you can model smaller things. And because it is based on category theoretical concepts, you can compose these models together to form bigger models. So here you're seeing that there is a subsection of this model, and there is another model here, and both of these can be composed. And the way to compose is that you join links here, and there are gray areas here which are called sites. So this goes into this goes into this, and all the links join together to form a bigger model. And there is a mathematical notion of composition here, because the interfaces of the bigraphs have to match and things like that. But we are not really going there. I want us to understand the intuitive view first, and then we can go into the maths if required. So this is the composition here of this is basically how bigraphs can be composed. And the idea is that you can make bigger models from smaller models, right? There are other operations also in bigraphs, which you see. So you have to look at it from an algebraic point of view, in the sense that it defines a very rich algebra, and it has his history in process algebraic notions in computer science, like CCS and pi calculus and so on. So it's something like this, that you have got a set of numbers like integers, and then you have got operations like plus and multiplication and things like that. Similarly, you have got bigraphs, and you have got these operations to combine bigraphs and divide it, so on and so forth. So bigraphs has a rich anatomy. And the other thing that you can do is, one way to represent bigraphs is this. That is a graphical way. But there's another way of representing bigraphs, and that is through equations, right? And the advantage of doing this is that a computer can understand this better than the graphical structure. Okay, it's just like, I mean, if you want to program using a bigraphical reactive system, you can have this as a language which represents this. So this has a room full, which has got a room within which we have got an agent and a computer. So things like that. So you can represent that using scripts. So when we talk about bigraphical reactive systems, we have got bigraphs that represent the statics of things, and reaction rules through which you can specify dynamics. So it's just not, bigraphs have been used to model a lot of things, like, for example, giving semantics to programming languages in computer science, biological systems, right? Network protocols, and a lot of other things, right? So this is basically a meta modeling framework that we are doing. So why we are doing this and why is it interest to this particular community is that the existing formalism to model a building is that of BIM, right? But BIM alone cannot be used to model dynamic aspects within a cognitive building, because BIM can do the structural aspects of a building, but to do dynamic aspects of a building with respect to which has maybe sensors, actuators, and things like that, you need to have mechanisms on top of BIM which can model those behaviors. And that is where this work comes in. So the first thing that we proposed was a model called actors at BIM. And the act between actors and BIM is that these actors are within a BIM model. Okay. And the big picture of this is that actors are basically, again, a model of computation. So for this community, we can think of actors as a block in Rhino, which has some input, it processes it, and it can give some output, right? So these are basic models of computation through which you could design systems. It has got certain formalisms. It has other aspects to it in the sense that an actor can create another actor. An actor can manage another actor. And you can send messages between different actors to perform different kind of things. Okay. So the actor in this particular model of actors at BIM are responsible to model the sensing, computing, and actuating aspects of the cognitive building. And the BIM is basically for the structural aspects of the building. And what we have achieved is that we have been able to use biographical reactive system as a meta modeling framework to model both actors and BIM in a cohesive way, so that the sense, compute, and actuate, or the cyber aspects of the system, are being managed by the actor model, and the BIM or the spatial aspect is managed by BIM. We are not tied down to BIM. It could be any other formalism that we could use. It could be things like space syntax or any of those things. But we started with a very small building level arrangements to understand how things will work for us. Now, the actors at BIM is basically a hierarchical model, wherein we are able to derive modelings for specific devices like sensors, actuators, to a level of digital twin, which represents the entire building in its entirety. And this was the work that we presented last year, in the last edition, I mean. Okay. Now, how the BIM layer comes in is that we have a BIM server wherein the BIM model is placed, and we have a BIM actor, BIM query actor, which integrates very closely with the BIM server. And it can change the BIM model to some extent by using custom tags. So for example, if there is a room within the BIM model, and we want to say that, okay, the temperature of this room is 5 degrees centigrade or maybe 20 degrees centigrade, we can use some custom tags, and we can set that the sensor has sensed the temperature of this particular room at this particular degree centigrade, so on and so forth, or whether a door is open or a door is closed, what is our arrangements, things like that. So all these are using the BIM query actor along with the open source BIM server that we had used. Now, this is not the first time that bigraphs have been used in such kind of a situation. There's an earlier work wherein the actor model and bigraphs, which were representing space, was used, but they had used different semantics. So they had used structural operational semantics for modeling actors and the biographical semantics to model space. But engineering tools on two different type of semantics are different, and what we wanted was to have the same meta model to model both of these. There was another work which was more towards how BIM and bigraphs can be transferred. So given a BIM model, how do you transform into bigraphs? But here, the notion of an agent was not very clear as to what the agent would do. So the extension to this work was that we have formalized what an agent could do specifically with respect to the actor model of computing in computer science. So basically, we augment BIM with, so what actor model basically achieves is that it augments BIM with sense, compute, control for cognitive building use. Now, the actors at BIM model, as of now, could not model safety. And that is what the extension that we are proposing here. And what we are trying to do here is that we are trying to incorporate dynamic fault trees, which are formalisms to model safety within this particular framework. So this is the notion of static fault tree, which is basically a precursor to dynamic fault trees. And what this basically tells you is that there are two kinds of gates, the AND gates and the OR gates, which says that, okay, there can be ignition if there is smoking or sparks or a short circuit, and the probabilities of them are given below. And the ignition happens only if there are combustibles and the fire is out of control and there is ignition. So you can actually model the safety scenario using static fault trees. And this is a probabilistic model. And what you try to find out is that what is the probability of the plant burning down. Okay, this could be used in buildings. This has been used extensively in automobile space, wherever safety is critical. But this could not model certain aspects like temporal failures or things like, in bigger systems, there are always pairs. So for example, if there are, a server which is acting as, within the cloud, you may have more than one server. So if one server fails, the other one takes out. So all these redundancies and things like this could not be modeled using static fault trees, and the things evolved to what is called as dynamic fault trees. And in dynamic fault trees, what we have is we have more number of gates, which can have things like sequential failures, which can model pairs, and we can have things like functional dependencies and things like that. So basically, functional dependencies means that if there is a trigger event and there are other events which are auxiliary to it, if the trigger event fails, all these events fail. So something like, for example, my computer is connected to this particular power plug, and if I remove the power, the system can come down. So that could be a trigger event. So modeling all these kind of things is what dynamic fault tree does. And what we have done is that it's not the first work that models dynamic fault trees, but our contribution is here. We give a new representation of dynamic fault trees using biographical reactive systems, and this is for the first time that this has been tried. There are other formalisms that has been done to model dynamic fault trees. But what we are trying to achieve is that we are using biographical reactive systems, and we are using a set of different formal models, which the biographical reactive systems is able to model. And we are combining these models to form newer models. So for example, here we have BRS, which models BIM, which models actors, and which models dynamic fault trees. And what we can do is we can combine these kind of models to form actors at BIM. And then going forward, we can have more such combinations. And these combinations are also formalisms. And they have a deep-rooted structure in category theory. So you can combine actors and dynamic fault trees to say how faults are being transmitted from one gate to another and things like that. You can model things like ontologies. So what happens is that you have got a set of models. It's not just one model that is targeting the cognitive building. It's a set of models, each which is being specialized for a very specific modeling exercise. You are combining them such that the tools at the topmost level, which has been the tools, the results, and everything that has been researched at the topmost level can boil down to each of these derivatives. And this is the advantage of the biographical reactive system as compared to other formalisms that has been kind of considered before. Apart from this, we are also worked in a tool which is called BigBIM, which is basically a modeling mechanism. And there are some extensions to this from the previous work. So what this basically does is that you can take in a BIM model, which is in the IFC XML format, and there is a BIM to bigraph converter, which uses building ontologies like bricks and others, and the building smart dictionary to convert an IFC XML model into bigraph. And from there, you have a modeling language called Blang, which is basically a domain-specific language for designing bigraphical reactive systems. Now, there are two languages which are derived out of it. One is actors at BIM, and the other one is DFT, which can be compiled back to Blang. And from there, you can convert it into a notion called into a language called Prism, which is basically a tool to do probabilistic model checking. So what is model checking? So model checking is used to find out if now how are software tested? So you build a software and you have a testing team which tests, but the way testing works is that a tester will tell you that a system has a bug or not. He or she can never tell whether the system is bug-free, right? So formal modeling is a mechanism which is used in safety critical system through which you can prove that your model is bug-free, right? And the way you do is that you have a modeling language which has got a very strong semantics in terms of how things behave, which is mathematical. And you convert that into something called as a label transition system. And this label transition system is basically a set of states and how these states can be arrived. So it's similar to kind of reaction rules that we have in bigraphs. And then that can be analyzed through a tool called a model checker using logics like linear temporal logics and others. And what the model checker tells you is that whether a property that you're testing is satisfied or not. So if you can test whether my system has deadlocks, for example, or other properties, whether a door will open within 5 minutes of a fire, things like that, right? So the model checker will evaluate the state space, and it will give two results. One is whether the thing is satisfied, or if there is a violation, it comes out with a counter example as to where things have failed. And then you can go back to your design and then change it. And you can do this in an iterative fashion till things are successful. So this is the domain-specific language which is there. And this is ID agnostic. So this is Eclipse. This is VS Code. And there is a diagramming extension to it also using Sprotty. So you can have a biographical reactive system, the sample, diagrammatic representation comes on the left-hand side. You can change the diagrammatic representation, the code automatically changes. And this has got verification support for Prism. So if you want to look at and we want to place this within a framework, this is the framework that we are using, which is called Viewpoints, Formalism, Languages, and Tools. So basically, we have got viewpoints. Viewpoints are basically pain areas of the end users, and which are supported by some kind of formalisms. And these formalisms are implemented by certain languages and tools. So for cognitive building, these are the viewpoints that we have covered till now. This can still be evolved, and that is where we are looking for collaborations. So the viewpoint of building geometry is covered by bigraphs. BIM. The modeling of cyber-related functions are captured within actors and BIM. Safety reliability aspect is captured within DFT. And all these formalisms are meta-modeled using biographical reactive systems. And then there are languages and tools which works across these particular formalisms. So these are the future work that we plan to do. We would like to consider other formalisms, specifically space syntax and others. We would like to explore how do we put in ontologies into it, because ontologies also has these kind of structures so that agents can, we give a formal mechanism for agents to reason. And we would like to extend the language tool suite and focus more on the graphical domain specific modeling aspect. So Thank you. That's Should I be closing this or?
So the second paper, it's named Formal Methods in Flood Disaster Response, the case of Porto Alegre in Brazil. It's by Ana Paula Dalcin, Camilla Pezzica, Clarice Bleil de Souza, Diego ALTAFINI e Guilherme Marques. I'd like to invite you to come here and present your paper.
I'm here already.
Oh, you're here. I was so concentrated.
Don't worry. Thank you for the presentation.
Oh, yeah.
So presenting myself, I am Diego ALTAFINI. I am a Marie Curie Fellow at the Welsh School of Architecture. And as presented, I will present you a bit about formal methods in flood disaster response and the case of Porto Alegre, Brazil. So climate change is increasing the recurrence and severity of floods and extreme events, especially in urban areas, such as those we had throughout Wales and England in the last week, as we had in Valencia, Spain, and as we had in the case that I will present to you today. So in May 2024, torrential rains have drenched the state of Rio Grande do Sul, Brazil, and triggered the floods, worst floods in 80 years, which affected 91% of the municipalities of that state. This rainfall was so intense that it surpassed in 48 hours the 500 millimeters, meaning that we had columns of water of more than 5 meters on some places. These floods displaced more than 580,000 people and really disrupted the road circulation network on between the state capital and the metropolitan region, and erased from the map cities, entire cities. So just to give you a dimension of these floodings, here we have a Sentinel-2 image from 18 April, and this was the state after the floodings, after 8 May. The interruptions on the road system posed a very difficult challenge for the coordination of the relief services due to the multi-scale collapse of the road network system. In that aspect, the formal methods of architecture, such as configuration analysis that interprets roads as graph networks, played an important role in conjunction with other knowledge domains to actually provide actionable information to the stakeholders and to the responders to cope with this crisis, as it's described the system performance before and after. So this presentation will provide an account of these efforts that we were involved at Cardiff together with people in Brazil, and demonstrate the performance shifts in terms of relative accessibility and preferential routes within the Porto Alegre metropolitan area. And we will also showcase how we communicated these results as a decision support system pilot, which was co-designed with both local researchers and through the engagement with the local authorities. So we could actually showcase the important aspects of the models themselves. So just to introduce and provide an overview of the analysis area and the conditions where it's stable. This road network graph derives from OpenStreetMap. It's the base of comparison among all the scenarios that we established. We established 4 scenarios, we'll go in detail later. And this represents the extent of the most affected urban area from the floodings. This map was generalized to remove those elements, those road elements that were deemed as, not unsuitable, but that might distort the actual analysis, because those were or flooded preemptively because they are unpaved, or are rural roads that do not are usually not used in this kind of accessibility models, as they would be blocked anyway due to the rain. And here I can showcase you the most important access. So we have several roads that are considered highways, especially the BR 290 and the BR 116 and the RS 180. Those are very important axes of structure, as you can see within the system. This is what we call scenario 0. We have 3 scenarios post-disaster. This is the scenario 1 that represent the road conditions immediately after the floodings. So from before 6, in fact, to 8th of May. We consider 6 because the flooding mark was validated for the day 6, for 6th of May. And you can see that we have several interruptions, but here on the bottom, so all the roadways of the BR 290 are cut away, and up there we have the cuts on BR 116. Also, several access between Porto Alegre and this northern part of metropolitan region were severed, and towards both northeast and southeast. These blockages create 3 independent systems, as we'll see later on. In scenario 2, we simulate a hypothesis of the RS 180 interruption and the total collapse in terms of connectivity between the southern and northern part of the metropolitan regions. This would result in 4 independent rural networks. And this was a very important risk because that roadway was within the flooding mark, but was a bit elevated. So if the waters rise another meter, probably it would lead to the general collapse. So that area was very important because, as you see, is the only connection. And it needed interventions in terms of safeguard of the whole structure. And we have scenario 3 that is after 10th May, that represents the emergency corridor opening. So we reconnect the center of the Porto Alegre city towards the rest of the metropolitan area. Because the problem was this area here is left inaccessible in the scenario 1 because we had interruptions here and no other access towards the other. So the emergency corridor was made around here and relinked the elevated highways that remained inaccessible in the original or in the initial part of the disaster, right? So there is the emergency corridor. It's added a bit of redundancy to the system, right? Each system scenario is modeled using angular segment analysis, a methodology from Spain syntax for the measures of normalized angular integration and normalized angular choice. And we go to describing a little bit of these measures right now. Well, normalized angular integration measures the relative accessibility from a road element toward all the others in the system. Therefore, it gives us the dimension of the movement potentials within that network. This at radius n. When we use metric radii, those denote the local relative accessibility that can be associated to certain transport modes, depend on the radii, such as pedestrian and vehicular, and measure the movement potentials at those scales. The other measure, the normalized angular choice, measures the number of times a certain road element is traversed to reach all the others within the system, thus indicating what are the preferential routes for moving from one part of the system to the other. And of course, the probability of flows within those roads. At the local scale, it more or less indicates the same thing, but also in terms of neighborhood scale and associated to certain transport modes. Well, onto the results of this analysis. In total, around 12.8% of the system was flooded. Despite this doesn't apparently to be much, it's a low percentage, it's just a bit more than 10%. This interruption caused a very noticeable drop in the system performance in now post-disaster scenarios, especially regarding relative accessibility. So here we can see individually the scenarios, and we can have a more precise dimension on what this occurred. So in scenario 1, we had the greatest loss in terms of road network performance when we consider especially system-wide relative accessibility, so 9. And the average values dropped to 48% of the stable system. The stable system is the black bar on the top that represents the 100%. So every system is related to that one in terms of average 9 distribution. In scenario 2, we had a lower decrease, but as we soon observe in the maps, this is due to the relative accessibility patterns concentration and not an actual better system performance. Because since we have 4 systems and those systems concentrate the relative accessibility in themselves, they tend to be higher in that aspect. Scenario 3, which would be the scenario with the development corridor instead, we actually have a real improvement of performance with the connection of the emergency corridor. Okay. So how these results are translated spatially? First, let's start with an overview of the stable system. You can see that the movement potentials are evenly distributed between north and south. We have the centrality core, which is the red road elements, well distributed among all the municipalities of the metropolitan network, and we have 5 or 6, if you count differently, connections between both east side municipalities and north side municipalities, right? So the metropolitan system is established within the 6 points of redundancy. When we have the interruptions, you can see that there is a devastating impact on the movement potentials across the metropolitan network, which especially affects the Porto Alegre city center. You see, it basically erases the high accessibility that we had there before. This is caused because we lost basically all of the accessibility points within the road circulation network, the highway network. So the only one remaining is the RS 180. This greatly affects this region because especially those areas that flooded both here and here are also the areas where we have a very high concentration of a low-income population. So besides being a network impact, it also had a very big social impact. Moreover, another thing that is important to point out is that this region that was flooded is the Porto Alegre airport. So the Porto Alegre airport was flooded and we could not receive relief efforts through here. The only airport that was working is located here and is the military airport. So imagine that to the relief services arrive at Porto Alegre, they would need to cross the RS 118 and go throughout all the system like this. So it was a very difficult effort in terms of relief and such. So regarding the northern areas, the only access remainder was through the RS 020, which is the one that is highlighted, and it segregated the whole northern area. So access towards these areas here was way how can I say, the access was very impeded, as we can see. So you had to basically do all that route to arrive there. So it remained really segregated just because of the interruption here and the lack of redundancies. And moreover, the municipalities of Montenegro and Guaíba were isolated from that system, so we could only access them by boat and provide relief services by boat. And the municipality of Eldorado do Sul, which was here, completely disappeared because 100% of its road network was flooded. So basically, they were hanging on the 2-star buildings. Well, scenario 2 works with the hypothesis of the cut out RS 180. So you see that we form for different and contained systems. The relative accessibility increases in terms of performance because Porto Alegre becomes its own system, right? But in the end, it becomes isolated from the logistical hub that is in the other side of the river. In this sense, you would have to go more than 100 kilometers through roads on the bottom to be able to arrive from there and there, because the only access is towards the seaside areas, the coastal areas, which it's rather far from Porto Alegre. So in that part of the system, we could even not model it because it will probably be irrelevant in terms of relative accessibility between those two places. It's too much of a distance. So one thing that we must consider in that aspect is that small disconnections can have a very big impact on the relative accessibility. So as you see, it increases on other parts, but it decreases in general. So also you can see that this scenario is very close to the 5 kilometer scenario. Basically, both these two systems become local, so and not function as a global entity anymore. Well, in scenario 3, we inform how the system actually improved with the inclusion of the development corridor, because we can see over there that it becomes very similar with what we had before, especially between Porto Alegre and the middle part of the metropolitan region. Of course, the northern parts continue to be segregated because we do not have other redundancies to connect there. So there is that. So the emergency corridor tends to improve the system. This was the emergency corridor, so it connected that part, which was pretty flooded, which I think it has more or less 1.5 meters of sediments that we were used to make the emergency road. It improves the movement potentials in general and the linkage between the Porto Alegre area. So the system-wide impacts in preferential routes tend to be more limited in general because of the probabilistic nature of this measure, and that the hierarchies tend to be maintained despite perturbations in the network. In this case, the performance improvements or deteriorations are dependent on the elements that are disconnected and do not impact in the system-wide movement as the relative accessibility measure, right? So all three scenarios remain pretty much similar in terms of what are the preferential routes in that aspect. So restoring one of the preferential routes, of course, will give the system a bit more of life or more of performance in that case. We could see even in the graphs that they were pretty close in terms of general performance. And well, so how these analyses were used to decision support? In the context of post-disaster, we engage with different figures of the public sector in Porto Alegre to communicate the initial results, because these analyses were made between 1 and 3. So in the very early beginning of the disaster. And to showcase, well, how it affected, right? How this analysis can help you. And we actually interface with them to see which were the most critical issues that were, of course, guaranteeing the access to relief efforts. So guaranteeing the north and south accessibility, right? In that sense, we created this communication, which was distributed to the high-ranking officials that were informed that they needed to all costs preserve the connection between the two. After that, we did the technical note. And recently, we made another communication showcasing the whole analysis that was used to also create this paper, right? So to finish this presentation, some concluding remarks. This was a showcase of how the formal methods can be instrumental to support decision in the context of floodings, which can also be transferred to other kinds of natural disasters that affect specific urban areas. In specific, the configuration analysis is a great asset, providing an overview of the network conditions that impact both accessibility and routing, which are crucial to relief actions. So these scenario-based comparisons, especially founded on cartography, allow non-experts to quickly understand the criticalities and raise their awareness for the impacts and decisions to be made. Yet there are a couple of challenges in that, especially regarding computational demands that still limit the real-time application of these formal methods in larger scales. These models took 3 days to be made, and 3 days in that context is a lot of time. And furthermore, we need to have a more tailored decision support framework as communication of these results need to reach non-experts. And these decision support systems need to be outcome driven or need to be tailored to their understanding. Otherwise, they will not act on this information. Thank you for the time. Sorry to have a little bit abroad time.
For now, for a period of questions and discussion, I would like to ask you to join us. So we have these two very different. No, the first one is not come.
Okay.
Yeah. So, so these are two very different papers. With one basic topic, which is fire and water. Yeah. So I'd like to ask if anyone wants to put some questions.
I'd like to ask a question to Govind. I was specifically interested in you present this framework with the different models. You have the BIM model, the actors model, the FP model, and then you combine them. And maybe you could shed a little bit more light on how you combine them. Is this through hypergraph, or I mean, how do you integrate the different models?
Yeah. So the integration happens. Yeah. So the integration aspect happens at two levels. One is because we are using the same meta modeling framework, we are able to model this using similar building blocks. So one integration is at that level. The other integration is more at the category theoretic level, wherein we use things or notions like refinement. So there are notions in category theory which talks about horizontal and vertical refinement. So if you look at it, these models are basically specializations of bigraphical reactive systems. So they are like a vertical descendant of bigraphical reactive systems. So they are like a vertical refinement. And if you look at things like actors and BIM, right, they are like horizontally apart. But you can use the notion of composition in category theory to compose the actor model within, something like BIM. So the notions from category theory comes very beautifully into this, because the advantage is because of the meta modeling framework that we are using, which is bigraphical reactive systems. And it has got a very strong background in the category theoretic framework, specifically because it forms what is called as a symmetric partial monoidal category. So because of that, this is something which is inherent that we get out of. We get out of it fairly easily. Yes.
This is also for Govind. I'm wondering, how are you planning to validate the model or the actors?
By validating, you mean what exactly?
Or
Oh, okay.
regarding-
the paper has got examples of validation. The validations that we have used is specifically validating the biographical reaction rules with respect to the expected behavior of the dynamic fault trees. So the dynamic fault trees have got, so dynamic fault trees are a set of gates, right? So like a priority AND gate or a sequence gate and things like that. They have got a specific behavior. What is there in the paper is that how those behaviors are being captured using biographical reaction rules and a formal verification mechanism, which formally verifies that indeed the representation, the biographical representation follows those rules. So that is one level of validation formally, which is presented in the paper. But what we are interested is basically how it can be used within this particular community. So the validation from the users is something which we are more interested in.
Thank you. I have a question for, or maybe a comment or a suggestion for Diego. You looked into the impacts of a disaster that sort of cuts off connections. And now you focused a lot on the integration and choice values that are used in space syntax, which are important to understand flows and important to understand, let's say, centralities and activities that will take place. But maybe it's not so problematic if actually temporarily you have let's say, it's kind of a segregated system or 4 systems, as you said, that are working in themselves, if the main services are still accessible, or if the distance to those sort of crucial services, let's say hospitals, or let's say are still in place. So I would suggest actually to add, because you have the model, to add accessibility analysis to those kind of crucial, that the stakeholders can help you find, let's say, the crucial services.
Yes.
And see how, let's say, what is the increase in distance to those. And then you can also add, if you have the data, the magnitude of, let's say, the amount of people that are actually impacted by that. So you get a kind of another understanding, because maybe actually, yeah, one bridge or one road that disappears, if you can take a detour, yeah, the system is kind of not so well integrated anymore, but that's not a problem for those 2 weeks, let's say, that you're living after the disaster, if the distances are not too big and if there is still accessibility, etc.
Okay, no, this is an excellent suggestion. They actually did this on the grand scheme of things, because we supported an effort that was multidisciplinary, that was conducted by the university in Brazil, but they didn't have the expertise nor the time and nor the computational power to actually model those data sets. So they actually did the accessibility analysis on their side. We focus here on what we did. That's the main thing and the main take that we had on this paper. And do not also focus it on all things we did, because we also did the redundancy analysis using the methodologies of Valerio, basically. But we did not include in this paper, as it will be too much, because this was an effort that resulted in more than, I don't know, I think it was 42 or 43 maps, counting all the scenarios and all the analysis. So it was impossible to actually present them on the paper. But they actually did both relationships with the populational analysis, the demographics, and it will be published in the next paper that we are still working on with the people in Brazil. And they did cross those data sets with both the temporary shelters, both with the hospitals and the schools that were used as temporary shelters, of course. So in the end, there was this crisscrossing, but we just do not focus it on this work. On the thing being temporary, well, this is a bit of a stretch to say, because in the end, the situation was normalized around June. So it took more than a month basically, to actually return to the stable system. So it was a pretty much ongoing disaster. But thank you for the suggestion. I think it's very interesting, and we should have a look also in publishing those results.
It could also be, let's say, maybe you should compare then these results. Is it a kind of a good indication that your analysis gives, that you don't have to do all the other ones, to sort of find what is the minimum of set of analysis to get a good overview of what are the consequences? That could be also a next step if you already did all the other ones.
Yeah, in terms, sorry, you can continue. Sorry.
No, I don't have more
Okay,
questions for you.
no. In terms of local, that's why I didn't even show the local maps. In terms of local, the system was not affected that much because we have a rather contained, how can I say, flooding towards the residential areas. That we're not actually affected the areas that we had the concentrations of services in Brazil and in Porto Alegre in general. The great problem in that aspect there was the airport, because when the Porto Alegre's airport was flooded, we could not land the planes with the relief aid from outside. And getting the relief from the coast, the seaside of the state, it's a very big endeavor because it's more than 120 kilometers. And there are actually roads that were unaffected in terms of, how can I say, general blocking, because this was the area that was most affected. But as I said, 91% of the state was affected in some way or another. So we had blockage throughout all the state. It would be very interesting to actually model the whole state system. But as you understand, this is a computational impossibility almost. But again, thank you for the suggestion. I think it's very useful, and we'll look into it for sure.
Very well. So does anyone else wants to make a question? No? Okay, then thank you very much to the authors. We're going to start with the other section. Yeah.